Well, welcome back to our class on software engineering. This will be the last video for the fourth section on software management and actually the last video for the course. And so this will be a chapter on configuration management. And the four things that we'll talk about in this lecture are version management, system building, change management, and release management. So configuration management is concerned with the fact that software systems are constantly changing during development and use. And as a result, configuration management is concerned with the policies, processes, and tools for managing changing software systems. You need configuration management because it is easy to lose track of what changes and component versions have been incorporated into each system version. And configuration management is essential for team projects to control changes made by different developers. So the CM or configuration management activities, there's a couple of them. There's version management, system building, change management, and release management. Version management keeps track of the multiple versions of the system components. System building deals with the process of assembling program components, data libraries, and compiling them to create an executable system. Change management keeps track of the requests for changes to the software from customers and developers. Release management, it prepares the software for external release and keeps track of the system version that have been released for customer use. Here is a drawing of the configuration management activities. So you see the various things, the components, the system versions and the system releases and the various things that are involved with each one of those things, as well as the change proposals. For agile development and configuration management, agile development where components and systems are changed several times per day is impossible without using configuration management tools. The definitive versions of components are held in a shared project repository and developers copy these into their own workspace. They make changes to the code. They then use system building tools to create a new system on their own computer for testing. Once they are happy with the changes made, they return the modified components to the project repository. For the development phase is where the development team is responsible for managing the software configuration and new functionalities being added to the software. The system testing phase is where a version of the system is released internally for testing. And finally, a release phase is where the software is released to customers for use. For multi-version systems, for large systems, there is never just one, quote, working version of the system. There are always several versions of the system at different stages of development. There may be several teams involved in the development of different system versions. Here is an illustration of the multi-version system development process. And you can see there's multiple versions that are going on, and you can have sub-releases for each one of those. For terminology, you can go ahead and look at these at your leisure, but here are some of the terms: baselining, branching, code line, configuration control, configuration team or software configuration item, and mainline. These are the first of the 2 pages. There's merging, release, repository, system building, version, and workspace. For version management is a process of keeping track of different versions of software components or configuration items in the systems in which the components are used. It is also involved in ensuring that changes made by different developers to those versions do not interfere with each other. Therefore, version management can be thought of as a process of managing code lines and baselines. A code line is a sequence of versions of source code with later versions in the sequence derived from each version. Code lines normally apply to components of systems, so there are different versions of each component. The baseline is a definition of a specific system. The baseline therefore specifies the component versions that are included in the system, plus the specification, libraries used, configuration files, etc. The baseline may be specified using a configuration language, which allows you to define what components are included in a version of a particular system. Baselines are important because you often have to recreate a specific version of a complete system. Here is an illustration of the code lines and the baselines and how those can relate. And so you have various code lines, the libraries, external components, and the main line, and have the couple examples of baselines being shown there. A version control system, the version control systems identify, store, and control access to the different versions of the components. There are two types of modern version control systems: centralized systems where there's a single master repository, and distributed systems where there are multiple versions of the component repositories at the same time. Git is a widely used example of a distributed version control system. What are the key features of version control systems? There's a version and release identification, change history recording, support for independent development, project support, and storage management. Public repositories and private workspaces to support independent development without interference. Version control systems are the concept of a project repository and private workspace. The project repository maintains a master version of all components. It is used to create baselines for system building. When modifying components, developers copy, that is, check out these from the repository into their workspace and work on these copies. When they have finished their changes, the changed components are returned, that is, checked into the repository. For centralized version control, developers check out the components or direct user components from the project repository into their private workspace and work on these copies in their private workspace. When their changes are complete, they check in the components back to the repository. If several people are working on a component at the same time, each check out it from the repository. If a component has been checked out, the virtual VC system warns other users wanting to check out that component that it has been checked out by someone else. So here's an illustration of a repository checkout check-in scheme and how that would work. For distributed version control, a master repositories are created on a server that maintains a code produced by the development team. Instead of checking out the files that are needed, a developer creates a clone of the project repository, then downloads and installs it on their computer. Developers work on the files required and maintains the new versions on their private repository on their own computer. When changes are done, they commit these changes and update their private server repository. They may then push these changes to the project repository. Here is what it would look like for repository cloning. You see how Alice and Bob are getting a chance to have a clone of the master repository as they're working on things. One of the benefits of distributed version control, it provides a backup mechanism for the repository. It allows for offline working so that developers can commit changes if they do not have a network connection. And project support is the default way of working. For open source development, distributed version control is essential for open source development. Several people may be working simultaneously on the same system without central coordination. As well as a private repository on their own computer, developers also maintain a public server repository to which they push new versions of the components that they have changed. Here is an illustration of how that open source development can work with the repository that, say, 3 different developers are working on. And so that gives you an idea how that would look. For branching and merging, rather than a linear sequence of versions that reflect changes to the components over time, there may be several independent sequences. At some stage, it may be necessary to merge code line branches to create a new version of the component that includes all changes that have been made. Here is an illustration of how we can have the branching and merging and the different code lines that could fit into that. And then you can see how ultimately there's maybe a branch and then eventually having to merge and coming back to a mainline copy. For storage management, this is when version control systems were first developed, storage management was one of the most important functions. Disk space was expensive, and it was important to minimize the disk space used by different copies of components. Instead of keeping a complete copy of each version, the system stores a list of different deltas between one version and another. So here is an illustration of the storage management using deltas. For storage management in Git, and as disk storage is now relatively cheap, Git uses an alternative, faster approach. Git does not use deltas, but applies a standard compression algorithm to store files and their associated meta information. It does not store duplicate copies of files. Retrieving a file simply involves decompressing it with no need to apply a chain of operation. Git also uses the notion of packed files, where several smaller files are combined into an indexed single file. Okay, let's talk about system building. System building is a process of creating a complete executable system by compiling and linking the system components, external libraries, configuration files, etc. System building tools and version management tools must communicate, as the build process involves checking out component versions from the repositories managed by the version management system. The configuration description used to identify a baseline is also used by the system building tool. For the building platforms, the development system, which includes development tools such as compilers, source code editors, etc. Developers check out code from the version management system in their private workspace before making changes. The build server, which is used to build definitive executed version of the system, developers check in code to the version management system before it is built. The system build may rely on external libraries that are not included in the version management system. The target environment, which is the platform on which the system executes. Here's an illustration of the build system. You have various things that are combined to work on the build as you're finishing up and getting ready to go to the next level in your development. What is a build system functionality? There's the build script generation. There's a version management system integration. There's a minimum recompilation, executable system creation, test automation, reporting, and document generation. For system platforms, the development system, which includes development tools such as compilers, source codes, and source code editors, etc. The build server, which is used to build definitive executable versions of the system. The server maintains the definitive versions of a system. And the target environment, which is a platform on which the system executes. Here is an illustration of the development, build, and target platforms and how they relate to one another. So you have a development environment, gets into a version management and building server, and finally that flows into a target system. For agile building, check out of the mainline system from the version management system into the developer's private network. That's how it's done. You build a system and run automated tools to ensure the system build passes all tests. If not, the build is broken, and you should inform whoever is checked into the last baseline system. Make the changes to the system components, build the system in the private workspace, and then rerun system test. If the test fails, continue editing. Once the system has passed this check, check it into the build system, but do not commit it to a new system baseline. Build the system on the build server and run the test. You need to do this in case others have modified components since you checked out the system. If this is the case, check out the components that have failed and edit these so the test pass on your private workspace. If your system passes its test on the build system, then commit the changes you have made as a new baseline of the system mainline. So here is an illustration of the continuous integration and how that would work. So you can see how this process slowly works through the whole beginning to end. So what are the pros and cons of continuous integration? For pros, the advantage of continuous integration is that it allows problems caused by the interaction between different developers to be discovered and repaired as soon as possible. The most recent system as a baseline is the definitive working system. For the cons, if the system is very large, it may take a long time to build and test, especially if the integration with other application systems involves. If the development platform is different from the target platform, it may not be possible to run system tests in the developer's private workspace. For daily building, this development organization sets a delivery time, say 2 p.m. for system components. If developers have new versions of components that they are writing, they must deliver by then. A new version of the system is built from these components by compiling and linking them. The system is then delivered to the testing team, which carries out a set of predefined system tests. Faults that are discovered during the system testing are documented and returned to the system developers. They repair these faults in a subsequent version of the component. For minimizing recompilation, tools to support system building are usually designed to minimize the amount of compilation that is required. They do this by checking if a compiled version of the component is available. If so, then there's no need to recompile. A unique signature identifies each source and object code version and is changed when the source code is edited. By comparing the signatures on the source and object code files, it is possible to decide if the source code was used to generate the object code component. For file identification, there's modification timestamps and there's source code checksums, and these are used to help identify where the files are in what type of releases. There's also what's the difference between timestamps and checksums? Timestamps, because source codes and object files are linked by names rather than an explicit source file signature. It's not usually possible to build different versions of a source code component in the same directory at the same time, so these would generate object files with the same name. Checksums, when we compile a component, it does not overwrite the object code as it would normally be the case when the timestamp is used. Rather, it generates a new object code file and tags it with the source code signature. Parallel compilation is possible, and different versions of the component may be compiled at the same time. So here is an illustration of linking source codes and object code. And so you have the time-based identification, and here is a checksum-based identification where you can see the code numbers that each one would have. For change management, organizational needs and requirements change during the lifetime of a system. Bugs have to be repaired and systems have to be adapted to changes in their environment. Change management is intended to ensure that systems evolution is a managed process and that priority is given to the most urgent and cost-effective changes. The change management process is concerned with analyzing the cost and benefits of proposed changes, approving those changes that are worthwhile, and tracking which components in the system have been changed. So here is an illustration of the change management process. And so you can see the product development, the development of the customer support. All of these are mapping into this process. So here is a partially completed change request form. I won't go through this, but this is something that's available that you can look at in more detail. And here is some additional details. What are the factors in change analysis? The consequences of not making the change, the benefits of the change, the number of users affected by the change, the cost of making the change, and the product release cycle. Here is an illustration of the derivation history that you could see what is in that particular version. For change management and agile methods, and some agile methods, customers are directly involved in change management. The proposed to a change that is proposed to the requirement and work with the team is done to assess its impact and decide whether the change should take priority over the featured plans for the next increment of the system. Changes to improve the software improvement are decided on by the programmers working on the system. Refactoring, where the software is continually improved is not seen as the overhead, but as a necessary part of the development process. What about release management? This is release management is a system. A system release is a version of the software system that is distributed to customers. For mass market software, it is usually possible to identify two types of releases: major releases and minor releases. So major or significant new functionality, and bug releases fix bugs that have been identified. For customer software or software product lines, releases of the system may have to be produced for each customer, and individual customers may be running several different releases of the system at the same time. For release components, as well as the executable code of the system, a release may also include configuration files that define how the release should be configured, data files such as files of error messages that need to be that are needed for successful system operation, an installation program that is used to help install the system, electronic and paper documentation describing the system, and packaging and associated publicity that have been designed for the release. In terms of factors influencing system release planning, there's competition, market requirements, platform changes, and technical quality of the system. And you can read about that at your leisure on this chart. For release creation, the executable code of the programs and all the associated files must be identified in the version control system. Configuration descriptions may have to be written for different hardware and operating systems. Update instructions may have to be written for customers who need to configure their own systems. Scripts for installation programs may have to be written. Web pages have to be created describing the release. And when all information is available, an executable master image of the software must be prepared and handed over for distribution for customers or sales outlets. What about release tracking? In the event of a problem, it may be necessary to reproduce exactly the software that had been released to a particular customer. When a system release is produced, it must be documented to ensure that it can be recreated exactly in the future. This is particularly important for customized long lifetime embedded systems, such as those that control complex machines. For release reproduction, to document a release, you have to record the specific version of the source code components that were used to create the executable code. You may keep copies of the source code files corresponding executables and all data and configuration files. You should also record the versions of the operating system, libraries, compilers, and other tools used to build the software. For release planning, as well as the technical work involved in creating a release distribution, advertising and publicity material have to be prepared, and marketing strategies put in place to convince customers to buy the new release. Release timing is also something that's important. If releases are too frequent or require hardware upgrades, customers may not move to the new release. If system releases are too infrequent, market share may be lost as customers move to alternative systems. For software as a service, delivering software as a service reduces the problem of release management. It simplifies both release management and system installation for customers. The software developer is responsible for replacing the existing release of the system with a new release, and this is made available to all customers at the same time. For key points, configuration management is the management of an evolving software system. When maintaining a system, a CM team is put in place to ensure that changes are incorporated into the system in a controlled way and that records are maintained with details of the changes that have been implemented. The main configuration management processes are concerned with version management, system building, change management, and release management. Version management involves keeping track of the different versions of the software components as changes are made to them. System building is the process of assembling system components into an executable program to run on a target computer system. Software should be frequently rebuilt and tested immediately after a new version has been built. This makes it easier to detect bugs and problems that have been introduced since the last build. Change management involves assessing proposals for changes for the system from the system customers and other stakeholders, and deciding if it is cost effective to implement these in a new version of a system. System releases include executable code, data files, configuration files, and documentation. Release management involves making decisions on system release dates, preparing all information for distribution, and documenting each system release. Okay, well, that's it for this lecture, and that's the last lecture in the series for the course. So with that, thank you very much.